The next thing we're going to look at here is theorem 7.1, which is the oh my, try again. You guys know, existence of inverse functions. Now, sometimes it's helpful to get all mathy on it. A lot of times I'm going to say, here's the mathy thing of it, and here's what it actually means. Because I think it's important for you to be able to read math definitions and interpret and figure out what they mean. That's an important skill to have in everything, right? Reading comprehension. Sometimes when you read math definitions and theorems, they sound, well, mathy. For a lack of a better word. They sound all mathy. So I want you to be able to be mathy with it, and then we can interpret what that actually is. So we're going to let f here be a one-to-one function on a domain D with a range R. Now I just saw that word domain looks a little like a wonky donkey there. Let's try it again. Okay, with a range R, then this function f that we have, f has a unique inverse. F has a unique inverse. F, and then to the little -1 power, that's the symbol for inverse, right? So f inverse with domain, there I go again. Domain R, and range D such that, I'm going to squeeze this in a little bit here, such that f inverse of f of x equals x, and f inverse, backwards. F of f inverse of y equals y, where x is in D and y is in R. Now here's the other beauty of these videos. If we were in class, I'd just keep rambling on, right? If you're in a video and you don't have something written down yet, pause that fella. Pause that fella. I'm not going to put a bunch of wait time in the videos because you have the option to pause them. So take advantage of the fact these are videos. If you missed something that I said, rewind it. Listen to it again, right? So this is the beauty of the video. So in these videos, I'm not going to do a lot of wait time. We're going to rock the socks off of this because I don't want to waste a bunch of time in videos, you know, like I am right now with this explanation. Okay, let's do it. Let f be a one-to-one function on domain D. So I'm telling you my input values are represented by the variable D with a range R. My output values are represented by the variable R. Then I know f inverse, because remember when you have an inverse function, you swap the x's and y's. So my domain now becomes these values that I've swapped out. My range now becomes these values that we've swapped out, such that your inverse, your f of x and your inverse, when you plug that in, those cancel out and I'm just left with that value. Same thing, f of f inverse cancels out and I'm just left with that value, where x is in D and y is in R. This is a fancy way to say you swap the x's and y's. This is what this says. You're swapping out that domain and range. That's a huge concept. A huge concept whenever it comes to inverses. All right? Because that's such a huge concept, then I want to make sure there's a whole theorem based on it, right? So I want to make sure you understand that concept because it is a whopper. Okay? All right. Let's take a look here at example 3. Yeah, I thought I was out of room. Let's go here to this next page. Example 3. Find inverse. of the following functions restrict the domain if necessary. Find the inverse of the function. Restrict the domain if necessary. Now here's the dealio, yo. When you have an inverse function, so I'm going to swing it back here for just a second. Here, what is the largest possible set that you can get an inverse? This whole thing doesn't have an inverse. This part does in particular, that I'm going, because we know this is a parabola going here from negative infinity here to 1. That is an inverse, so I can restrict the domain and just look at this side. I could also restrict the domain and just look at this side and that piece of it. Do you see that? Okay, so if here I'm looking at finding the inverse of a function and I can restrict that domain if I need to, it depends on what function it is that you're talking about. So here if I'm looking at A, I've got f of x is equal to a 2x plus 6. What is that? It's a line. Do I need to restrict anything for a line? A negatory, good buddy, right? So a line is a free-for-all. That's the beauty of the line. So let's go through the steps. Step 1, in order to find the inverse of the function, step 1 is to swap that x and y. So let's do that. The same thing here, this is the same thing as y is equal to 2x plus 6. We know that, right? F of x is the same thing as a y. So if I swap those out, I now have x is equal to 2y plus 6. Then step 2 is solve for that y. Okay, so I'm going to subtract 6, divide by 2. Now when I divide by 2 here, I'm going to divide every single piece by 2 whenever I have that, right? So when you divide every piece by 2, I now have this 1/2 x minus 3 is equal to my y. I like to write it, I'm going to squeeze this in just here a little bit, with that y on the left side, makes me feel better. And we know it's an equal sign, so it's the same. Then we're going to replace y with the inverse notation. So if I want to find this inverse function, we did that. And so this is really f inverse of x is equal to a 1/2 x minus 3. I don't need to go through here and restrict any domains because I don't have any issues because it's a line, right? So I'm not worried about that on this particular problem. Okay, just for fun, we are going to verify the inverse. Remember, when you have an inverse, like the definition just told us, if you input, let me go back here. If I do this input and restrictions here, if I input my functions, then I'm going to come out here with just an f of x. That's that composition, right? You can plug one into the other, and then that's how you can verify. Let me go back to black. So I can take f of f inverse or vice versa. You could put the f of x into it. Either way, you put one into the other into one. It doesn't matter. The process is the same. You're going to come up with x. Okay. So f of 1/2 x minus 3 means I'm going to take my original function and plug in that inverse and then see if I can just come up with x out of it. When you distribute this 2, the 1/2 times 2 gives me just an x. And then 2 times -3 is a -6 plus 6. And yes, indeedy. See that? So when I'm talking about inverses, this is all previous information into the current lesson, right? This is all, honestly, way back to your algebra. talking about inverse functions when you did that, bringing that into this current lesson. Finding an inverse function, verifying the inverse function. We haven't done any calculus yet. In terms of inverses, this is what we have. Let me click on this and make it bigger. The other thing that you need to be able to do is look at the graph. Can you look at the graph to determine that this is an inverse? Well, check it out. You've got this line, greeny here. This is your y equals x line. Inverse functions when you swap those x's and y's. So red is my original function. When I swap those x's and y's, then this is where it comes out. I've got the point here. Let's go blue. I've got the point up here of 0, 3, and I've got the point here of 3, 0. You can see that those are swapped, right? That's how you verify inverse functions with a graph. We can verify with that composition, and we can find it using algebra. We always like to start with a line because they're super easy. And then from there, then we can build on that. Okay, check it out. So we've got a line, but we all know that things don't last in terms of a line. So let's look at example 3b. I'm given f of x is equal to this x squared minus 1. Find the inverse function. Same thing. Function. Okay. So swap them out, x and y. So this is still y is equal to x squared minus 1. Now I have x is equal to y squared minus 1. So I'm going to add 1 to both sides. Look at what happens when I square root. Remember, anytime you physically make the square root symbol, you have to write plus or minus. And there, ladies and gentlemen, is where the issue happens. All right, that is where that issue happens. So because, and we already knew this was going to happen, because we know this is a quadratic and we just talked about it. So because we already knew that was going to go down, I just wanted to show you how that this was playing out. So this means it's not not 1 to 1, not 1 to 1. So restrict the domain. That's what's going to have to happen here. So I can have the positive or the negative. If we restrict the domain, and I know my vertex here is 0, -1 because of the fact that anything next to my x is going to be, this is in vertex form. This is 0 with the -1 in the back, right? The x values are all I'm concerned about. So if I restrict the domain and say that x has to be greater than or equal to 0, then I know my inverse function is going to be the positive that we have with that restricted. You see what I'm talking about? Okay, if I were to restrict it where x is less than or equal to 0, what would that be? Exactly, that's this negative part, right? Negative square root of x plus 1. So it just depends on how you restrict. You don't have to restrict it where x is less than 0. What do you need? What are you looking for? What does your data represent here? Let's look at the graph, because I always think that's helpful, is to looking at that graph. Then you can really see what we're talking about. I'll try to make it as big as possible so you're not super small. Here's my regular parabola. Let me get my... If I restrict it here, where I'm just looking at the positive, then I have this piece, blue to blue, right? If I restrict it here, where I'm just looking at the negative, then I have red. Both are legit. Literally, both of those can happen. It just depends on how you restrict that domain. So this domain is restricted if x is greater than or equal to 0, the domain, which puts me up here at the top. Here, if I come over here, let's go with the same colors. X is less than or equal to 0 if I'm looking at that domain, right? Then that's what puts me here for that restriction. All right. Okay. Now something else, anytime I'm looking at this and I want to look at some type of an inverse function that we have, let's say I want to go for blue. All right. If I were to graph this inverse function right here, just go with what we've got. So my blue function is this, where I'm restricting my domain where x is greater than or equal to 0. And don't forget, as I'm playing this out, I've got this y equals x that I have. I didn't draw that parabola very good, did I? Let me try one more time. Let me try to draw this a little bit better, because I want you to really see what's going on here. That parabola doesn't get too crazy. It goes more like this, right? Look how it's much more narrow coming up. I had it way out there. That one's a little bit better even. Look at that. I'm like a champion of the universe here. So this is my function, right? There's my y equals x line. And then my inverse that I'm looking at, where I have it down here as a 1, I know this is going to be at a 1, right? Because that's that inverse part. And then this is going to convert over like this. So if we were to take this graph, basically is what I'm doing, and I'm putting it here where I have that line. So I've got my f inverse and I've got my f of x. But you can see the same distance to that y equals x line. I've got this one here and this one here. Those x's and y's swap out. Do you see what I'm getting at? Okay. Inverses, right? Still just looking at those inverses.